Okay friends, welcome back to this class plate tectonics. So, in the last class we are talking about this crustal behavior, crustal nature, particularly the continental crust. And to add to this discussion, here we will talk about the rheology of the lithosphere, how the rheological properties of the lithosphere varies laterally and vertically, and what conditions there will be lateral variations. Either there is a fault zone, there is a collisional system, there is a rift system, or there is a boundary of this transition zone between this continental crust and the oceanic crust. So, we will discuss in this class. So, the behavior of this continental crust under the stress, it depends upon the temperature and the duration of the stress. For example, if you talk about this collision of India and Eurasian system, we have this stress from both sides, that means the Indian plate is moving northeast and the Eurasian plate is moving towards southwest, and how it will behave, this collisional zone, this crustal system, how it will behave there, that depends upon the temperature there. So, the temperature is playing a major role there to define what should be the crustal behavior, and the duration of the stress, whether the stress is long lasting or the stress is for a shorter geological time. So, that defines what should be the behavior of this continental crust under that stress regime. For example, if you see here, this is the dry lower crust mantle lithosphere and it is wet lower crust and mantle lithosphere. In dry conditions, if you see, we are having a granulite around 30 to 40 kilometer depth, and this is strong enough. Similarly, olivine, it is occurring below this moho and it is also strong and dry at the upper mantle existing. However, the same condition, if it is the presence of water, this is a wet condition is there. Now, you see, it is the strength increasing in this axis. So, if you see here, this is restricted up to this. So, that means the strength is up to this. So, that means the upper crust, it is behaving simultaneously or similarly as in case of the first image. However, once you are coming to this lower part of this crust, it is weak and wet lower crust we are creating. However, contrasting to that, here we are creating a strong and elastic lower crust, and if you see, the strength is increasing in this axis. Here the upper crust is less strong or it is weaker than the lower crust. You see, the strength is up to this level. However, here the upper crust is more strong as compared to the lower crust. If you are going beyond the moho, if you see here, this is strong dry upper mantle and it is high strength is there. However, here the strength is again decreasing. So, that means in the wet regime, the crustal behavior, it is gradually the strength decreasing from the upper to lower crust. However, in the wet region, this crustal behavior, it is like that the strength is decreasing from this upper crust to lower crust. However, in the dry regime, the crustal strength is increasing from this upper crust to lower crust regime. And the distribution of the strength with depth in the crust varies with tectonic setting. Then its strain rate, its thickness, this composition of this crust and the geothermal gradient. So, all these parameters that define how this strength distribution of the crust should be, and it is clear from these two images depending upon its dry and wet condition, and similarly the mineralogy also changes and the strength varies. Now, let us talk about the brittle ductile transition zones. In the brittle ductile transition zones, it is corresponding to an average surface heat flow of about 50 milliwatt per meter square. It is about 30 kilometer depth, which is also corresponding to the depth limit of the most shallower earthquakes. So, this transition zone here you can see it at around to 50 milliwatt per meter square, it is the heat flow is experiencing, and it is lying around here around 30 kilometer depth. Even in the lower crust, however, if stress is applied rapidly, it may deform by fracture, and likewise the pore fluid are present in the upper crust weakening it, and the stresses are applied slowly, the upper crust may deform plastically. So, that means there is no universal rule. Depending upon this stress condition, depending upon the duration of the stress and how rapidly or how slowly we are experiencing stress there, and the presence of pore fluid is there or absence is there. So, the lower crust may behave like a upper crust and the upper crust may behave like lower crust. So, that means even though the lower crust, if the stress is applied rapidly, it deform by fracturing. So, fracturing, it is a characteristic feature of the upper crust regime. However, the lower crust is behaving like upper crust if the stress is rapidly applied to there. So, this lower crust and upper crust, depending upon their conditions, pore fluid condition, rate of applied stress, duration of the applied stress may behave alternatively. For example, if the lower crust is stress is applied to the lower crust very rapidly, and it can be deformed by fracturing. However, the upper crust which having the pore fluid pressure, if it is slowly pressure is applied or stress is applied, it may behave plastically. So, that means the upper crust and the lower crust, their nature of deformation, that depends upon the stress regime, depend upon the pore fluid pressure, depending upon the how rapidly or how slowly this stress is applied to them. The regions of low heat flow such as shields and platform, brittle fracture may extend to the lower crust even into this mantle, because mafic and the ultramafic rocks can very resistant to plastic failure at this depth, and thus brittle faulting is very much common and the only way that can deform. So, that means this shield and platform, these are representing low heat flow regions. Rift basins, they are representing high heat flow regions. So, that is why if these regions, this crustal deformation occurs, the fractures are developed, these fractures can penetrate up to this lower mantle region or this mantle part, because the resistant rocks are there, they are very resistant to plastic failure. That is why brittle failure that can adapt very easily, that is why that can extend the fracture to this mantle or even to the upper mantle, up to this upper mantle. So, if you see here, this is the temperature and this is the depth and how this is heat flow, this is the dry solidus and this is the pyroxene geothermal field, and these are these regions how this geothermal system is varying. So, this shield area, if you see here, this shield area is representing the lowest one, or this is the region of low heat flow, that means low geothermal gradient is experienced here. So, the brittle ductile transition occurs at relatively shallow depth in a warm and young crust, it is around 20 kilometer depth. But if it is old crust, that is the particularly the proterozoic shield area is here, that is brittle ductile transition, that is occur around 30 kilometer depth. So, depending upon its age, either it is a younger crust or it is a older crust, the brittle ductile transition, as it is temperature dependent, the phase change is temperature dependent, that is placed either it is a shallower level or it is a deeper level, that depends upon the age of this lithosphere. The rapid increase in strength beneath the moho reflects chiefly the increase in olivine, which is stronger than pyroxene and these feldspars. So, once we are reaching this beyond the moho, there is a strength rapidly increasing. So, this is indicating the presence of olivine there, rather pyroxene and feldspar, which are relatively less strong as compared to olivine. In both cases, the strength of the ductile lower crust decreases with increasing depth, reaching to a minimum at this moho. So, that means the strength of the ductile lower crust is decreasing and it is at the increasing depth and reaching at the minimum at the moho. So, once the moho reaches, the strength again increases and that increment is due to this presence of olivine. Now, another point regarding the crust, that is called exhumation and cratonization. What is exhumation? Exhumation means which was earlier at the deeper level, now it is coming to a shallower level. This is called exhumation. And cratonization, that means amalgamation of cratons, crustal deformation and finally amalgamation of one cratonic part to another cratonic part. So, forming a full fledged craton, that is called cratonization. So, the exhumation, it refers to the process by which an area or rock mass that was formed or formerly buried, it is approached to this earth surface. So, this is the process of exhumation. Earlier the rock was at lower level, now it is coming to this upper level. If you see this figure here, this is the points where the deep metamorphic crust was there. Either there is a faulting and due to the faulting this system is going further down and this is further down, and here due to the stretching of the system this mantle is coming up and finally this metamorphic rock or high grade metamorphic rock which was earlier at the lower regime, they are coming near to the surface. Similarly, examination of the deep crust, if you can say this crustal material which is coming close to the surface due to decompression, due to releasing of the stress, particularly along these rifting systems where this crust is stretched. So, this mantle material it try to move up, try to expand. So, that is why it is coming up, that is called exhumation. So, exhumation is nothing by crustal deformation, by this exhumation of this mantle material, the lower rocks types which are earlier existing at the lower crustal level, they are coming close to this surface, that is called exhumation. However, it differs from this rock uplift and the surface uplift, that is explicitly measured relative to the surface of this earth rather to the reference to the geode. However, the exhumation is measured with reference to the geode. So, there is a local upliftment or there is a local subsidence, we cannot say it is an exhumation process. For example, suppose there is groundwater extradition and finally over exploit of this groundwater, this area is subsiding and the nearby area is uplifting relative to this, this cannot be called as exhumation. So, exhumation is a large scale process, it affects the gravity and overall system of this earth. So, it is affecting the geoid system, the gravitational system of this earth, that is exhumation. And mostly this is the density difference between the surrounding area and the area which is exhumed, because those rocks which are exhumed earlier which was residing at the lower crustal level, they are more dense as compared to the surrounding if it is coming close to the surface. The process by which cratons are formed, that is called cratonization. If you remember our earlier class, we are talking about this lateral accretion and vertical accretion. Imagine in the Precambrian time when this crustal thickness or the lithospheric thickness was very small, and due to the early phase of differentiation, we created some felsic crust of smaller size and they were randomly navigating from different directions and they are amalgamed with each other and finally the size increased. This process is called cratonization process. Though there is much uncertainty remains about this process, the first cratonic landforms that likely formed during the Archean eon and it is completed during the Proterozoic. Subsequent growth of continent was due to this accretion at this continental margin, like this India and Eurasia, they are colliding, that is accretion process, that is the continental margin. So, here one continent, another continent, and with time you see these two continents or three continents, they are amalgamated together, and this is representing a suture zone. So, that is why at present day, if you analyze this cratonic system, you will find number of suture zones existing. These are nothing, these are these areas or these are the lines through which these different cratons, they were amalgamated together during this cratonization process, and finally it is forming a full fledged continent or full fledged craton. So, during this continental collision, large segment of the continental crust, they are highly deformed and thickened, and later they are uplifted and eroded to form this craton, and this process is called crustal evolution. This crustal evolution, it is better understood, you can see from this figure here, this is the hidden time, and here this is the enriched RBSR crust, and this is the lithospheric mantle, the red color is the lithospheric mantle, and this is the hidden mafic crust. So, with time we are reaching from hidden to Euarchean time. What is happening is this thickness of this lithospheric mantle, it is increasing. Similarly, the thickness of this hidden or Euarchean mafic crust, it is increasing, and finally what we are creating? We are creating mafic volcanism, which is reaching from here to here, and with further increase of time we are reaching at the meso to Neuarchean, and finally what we are getting, it is the TTG crust forming, and this system, that is the dense mafic crust, is here, and some part it is going down due to this gravitational collapse, it is going into this mantle, and finally this is the full fledged cratonic composition. So, that means from the hidden time through Euarchean though Mesoarchean, the crustal system evolved both compositionally, both dimensional wise. It becomes thin to thick, and similarly in the two dimension, that is in the areal extension from small to large, and similarly compositionally it evolved from different composition to a different composition. So, this process is called crustal evolution, both size wise, composition wise, how the crust changed with time, this is called crustal evolution. And these crustal evolutions, they are imprint within the metamorphic rock, within the structural signatures. So, the structural signatures and the metamorphic signatures, they are better indicator of this crustal evolution, and followed by this magmatism. If it is there that different phases of the crustal evolution, they are ended with or they are accompanied with certain magmatism. So, that can indicate with the time sequence how when which time this crustal evolution that occurred. So, crustal evolution is imprinted in rock as a pressure temperature time trajectories, generally referred to as PTT path. It is pressure, then temperature, this is time. So, that means at what pressure it occurred, at what is the temperature that time, and when it occurred, this is time. So, that is why this time, temperature and pressure, these three components, they are studied for the studying or for the understanding the crustal evolution. Burial of rocks in the earth crust result progressive metamorphism with loss of water and volatiles, and producing almost anhydrous rock and the metamorphic rocks. So, here with if you see, we are going to a higher temperature regime from the lower temperature regime, and finally we are creating metamorphic rock relatively high grade into the depth. So, here with the slate, then phyllite, then schist, gneiss, then migmatite. So, gradually once we are going to depth, the degree of metamorphism increasing, and the metamorphic minerals assemblies may record the highest PT regime to which the rock have been subjected. Later examination make it possible to study this information directly. So, once upon a time those rocks which are at depth, for example, here this migmatite, it was in the depth. So, this migmatite, it has to come to the surface either due to thrusting or due to stretching. Once we are stretching, the system is coming up. So, either way, once it is coming to the surface, it is giving us these natural samples to study this PT regime at this depth. So, these are the ways how this crustal evolution can be studied. However, minor changes that occur during the retrograde metamorphism may be identified by studying the textural features. So, we know there are two types of metamorphism, prograde and retrograde. So, retrograde is nothing when we are reducing the temperature pressure. So, it is coming to retrograde metamorphism, and this retrograde metamorphism can be studied by the textural features. These textures are the key things that indicate how this retrograde metamorphism works on the rocks. So, using experimental petrology and oxygen isotopes data, it is possible to estimate the temperature, pressure at which the metamorphic mineral assemblage that crystallize, and the boreal depth of metamorphic terrain exposed to this earth surface can be estimated. For example, if you see here, these are these experimental petrology laboratories, how people are working, they are creating magma, they are creating these new rocks from this old rock with increasing temperature and pressure. Similarly, we are reducing temperature and pressure from the older rock, that means from the high grade rock they are creating the low grade rock. So, that means everything is understood through laboratory process. So, this laboratory process that can substantiate the field process that we are looking at the field from this oxygen isotope data and from the experimental petrology, these are substantiating to each other. So, minerals that form along different segments of the PTT path and become isotopically closed at a given temperature, and they are dated isotopically for add time to this event. So, time is very important event, like temperature and pressure. Time is very important event to determine when it occurred, at what geological time this crustal evolution occurred, whether the crust has evolved at one phase or there are different phase of evolution, finally the resultant crust is in front of us. So, that is why time is very much important, and different degree of this evolution or different phases of evolution, they leave different imprints that indicate when it occurred and what was the temperature and pressure regime. For example, if you see here, there are two PT path or PTT path is showing here. One is moving clockwise and another moving anti-clockwise. What does it mean? For example, here it is A. It represents the rapid boreal and uplift path, typical areas of continental convergence. That means it is a collisional system. Rapid boreal is there, less temperature is there. That means we are reaching at the highest pressure rapidly rather reaching at highest temperature. So, this is the characteristics feature of this boreal system, or this is a collisional mountain system. However, the other one, it represents heating and boreal in response to regional scale magma intrusion followed by prolonged cooling and slow uplift. These are representing the rifting systems, because magma is supplied below. Here temperature is more dominant than pressure. So, one is moving clockwise, another moving is anti-clockwise. So, two different PTT path that indicates two different geological condition, different geological stress regime, and this crustal evolution history. Diffusion experiment have confirmed a few mineral closure temperature, and those mineral closure temperature, they are crucial to determine at what temperature this occurred. For example, this argon 4039, that method can be used for the Hornblende dating, which closed the argon diffusion at around 500 degrees Celsius. Muscovite that closes at 350 to 400 degrees Celsius. K feldspar around 150 to 350 degrees Celsius. Fission track, which is annual to apatite, around 150 degrees Celsius. So, that means these are the closing temperature. If we have these minerals, by this closing temperature we can determine when this crustal evolution occurred, at what temperature it occurred. Thus, to unravel the PTT histories of the crust, it is critically necessary to combine the results from the field, petrography, experimental dating and the isotopic studies, because this laboratory experiment, laboratory data must has to substantiate with the field evidences. So, once they are converging and they are supporting each other, that means we have interpreted the crustal evolution rightly. Though cratons have long been recognized an important part of this continental crust, their origin and evolution are still not well understood. That is why we are doing so. Why we are going for this crustal evolution? Because we have not understood it clearly till yet. Though we have cratons starting from the Precambrian to recent, but still this process, how this cratonization occurred, how this PT path is behaving, we have not understood yet. That is why we are doing some laboratory experiment, some experimental petrology, we are going for a field and we are doing field works, we are doing thin section analysis, all these things they are converging together to study this crustal, to understand this crustal evolution. Most investigators agree that the cratons are the end product of collision orogenesis and thus they are the building blocks of the continent. Just how orogens evolved into cratons and how long it takes, however, it is not known yet. So, that is why we are continuously engaging ourselves to unravel this crustal history, the evolutionary history, how the system changed from one to another. Using a variety of radiogenic isotope system and estimated closure temperature in various minerals, it is possible to track the cooling histories of the crustal segment, and when is coupled with the geothermal this uplift and exhumation history can be established. So, even then the multiple deformation and metamorphism many poses difficulties and uncertainties about these complexities, because it is not one event, multiple events they are superimposed on one another. So, to understand that we have to gradually unravel one after another. So, we have to reduce the degree of uncertainty. So, that is why mineral identification and experiment and this field observation, all these things are very much necessary. So, that is why to unravel this crustal evolutionary history, the laboratory as well as the field that has to be combined together. Now, the PTT path of the collisional origin are typically clockwise as we have discussed few minutes back, and the PTT space and are reasonably well understood from the classic studies different mountain systems like these Appalachians, Caledonians, like the Himalayas, Alps, like that. So, here if you see, we are reaching the maximum pressure and before we are reaching the maximum temperature. So, maximum temperature we are reaching, for example, here the maximum temperature is here. Before reaching the maximum temperature, we are reaching the maximum pressure. So, how it is possible? That is possible due to this collisional system, because in the collisional system pressure is a dominant factor. So, we are reaching maximum pressure before we are reaching the maximum temperature. This type of PTT path results from the rapid crustal thickening, so that the maximum pressure is reached before the maximum temperature arrived. Hence, the metamorphic peak that is generally post dates early deformation in these orogens. So, this type of PTT path, it is very common in the collisional mountain system. The evolutionary path commonly leads to dehydration melting of this lower crust producing granitic magma, which is very common in collisional mountains, because we know this Ladakh batholith, it is a result of collisional mountains. So, this granitic magma, it is occurring due to dehydration melting of the lower crust and emplaced here. So, this dehydration melting, which is a characteristics phase or characteristics properties of this collisional mountain system, and which is the product is the granitic magma, and that leads to the emplacement of large scale batholiths along the collisional mountain system. Another one, it is the continental rift. It is the crust is heated from below by mantle upwelling before crustal thickening occurs, and thus the maximum temperature is reached before the maximum pressure is reached, and this produces a counterclockwise PTT path the metamorphic peak usually predates or it is synchronous with the early deformation in these cases. If you see here, we have a rift system and we are supplying this magma from below. Here temperature is playing larger role compared to the pressure. That is why this PTT path is like this, it is moving here, it is, this is the anti-clockwise system. So, that is why this counterclockwise system PTT path is observed in terms of rift basins, and mostly this metamorphic peak usually predates or it is synchronous with the deformation of these cases, because where temperature is reached at the peak much before than the pressure, and this is the characteristics of the rift system. Heating of this lower crust can lead to dehydration melting as a consequence of metamorphism and produce felsic magma, and any crust heating precedes thickening. The crust results in the counterclockwise PTT path. In addition to rift, that extended margin of the platforms, then magmatically underplated crust such as beneath the continental flood basalt have counterclockwise PTT path. So, not only the rift basins, so this counterclockwise PTT path, we have this extended margin of the platforms, then marginally or magmatically underplated crust, they also showing similar counterclockwise PTT path as the rift basins. So, in some instance, clockwise and counterclockwise PTT path, they occur side by side. For example, if we think about this subduction system and the back arc basin system. The subduction system, we have the pressure is more dominant here, and this stretching system, here the temperature is more dominant here. We are getting a counterclockwise PTT path here, however, we are getting a clockwise PTT path here. So, the counterclockwise and clockwise PTT path, they are placed side by side, and it happens and it is common in the subduction zone system where the back arc basin is actively being developed. Now, if you see these two images here, this is showing the cooling history of these two separate systems. In A, if you see, it is the overprinting of the post tectonic granite intrusion. Now, you see, this was the cooling history. Had it not been there, this peak is not been there. Suppose there is a granite intrusion here. At this granitic intrusion, so it was cooling like this, but due to this intrusion of the granite, this there is a deviation from this normal pathway of this graph. Similarly, in B, it is a complex multiple event of cooling history, that is final exhumation, it is S, and it is suturing edge in terrain A and B. So, we have this complex cooling history because multiple intrusions are there, it is not very simple. If you see here, it was cooling like this and finally, it is super cold here, then it is increased, that means there is an intrusion. Similarly, it was cooling very rapidly, but again there is an intrusion, then there is a constant, then it is moving like. So, that means I can say the crustal evolution that we talk about, it is not very simple thing. So, there are many phases of crustal evolution which was disturbed by magmatic intrusion, disturbed by metamorphism, folding, thrusting like that. So, due to that, it is not a simple history. The crustal evolution, establishing the crustal evolution history is not very simple, it is a complex thing, but the beauty of this system is that we have to take the help of the field as well as the laboratory suites. So, that this laboratory experiment result and the field observations both should substantiate each other to unravel the crustal evolutionary history. So, the result suggests a wide variation in cooling history of different continents. For example, if you see here, this is the origin having cooling rate mostly, that is 2 degrees Celsius per million years. However, there are some exceptions like this southern Brittany. If you see, it is this cooling history is showing greater than 10 degrees Celsius per million years. So, now if you see here, this is the southern Brittany, this one, you see this cooling history is very high, it is cooling very rapidly. However, all others they are following a particular path. So, this why this exception is there, why the rate of cooling somewhere it is fast, why the rate of cooling is somewhere which is very, that means normal. So, that depends upon this magmatic system and away from this convection system, that will be studied in detail in the next class, or when we will talk about the subduction and this convection system or the mantle. Some terrains such as this Interland and Antarctica have very long, perhaps the exceeding complex cooling history lasting over 2 giga years. So, this cooling history, as we have discussed, it is not same throughout all these continents. Some of these continents, some of these cratons, they are cooling very rapidly and some are cooling very slowly, and that depends upon many factors that will be part of separate class. So, many origins such as Gribenile origin in the eastern Canada have been exhumed as indicated by unconformably overlying sediments, which is reheated during the subsequent burial and then re-exhumed. So, that means it is not a single phase, there are many phases of burial, there are many phases of exhumation. So, a crust evolved through like this, it is not a simply that it is subducted and simply it is come back due to exhumation. Many phases of exhumation, many phases of burial that has undergone, and each phase of burial and exhumation, it leaves certain imprints that this research can unravel this crustal history of that region. Still, some important questions regarding the cratonization process, it is remain unresolved. The first is how terrain that amalgamed during continental continental collision evolved to a craton, because this is the terrains that evolved during this Precambrian time. How it became a craton, that is unanswered question. Does each terrain maintain its own identity and have its own cooling or uplifted history? Or alternatively, do the terrains annul to each other at an early stage and then the entire origin cooled and elevated to a unit? And what is the effect of this widespread post tectonic, that is platonism? Does it overprint or erase the importance of segments of origin cooling history? So, these are the few questions, they remain unanswered and people are working at different segments on it to answer those questions, and finally, you can say on not only daily basis, but monthly basis, new and new theories they are coming out, how the crust evolved and what should be the final outcome, that will be studied once the new research that adds new data and new understanding to the existing one. So, thank you very much, we will meet in the next class.